The first branch of physics we are going to study this year is mechanics. Mechanics studies what produces and affects motion. It is based on the work of Galileo Galilei and Isaac Newton. Mechanics is divided into two categories. The first is kinematics. Kinematics describes how things move without considering why they move. It's the how of motion, and it's based on Galileo's work. We're going to start the year with kinematics. The second category is dynamics. Dynamics describes why things move the way they do, and is based on Isaac Newton's work. So after kinematics, we'll move into dynamics. The first lesson of the kinematics unit is on position, distance, displacement, speed, and velocity. Before we start with position, distance, displacement, speed, and velocity, I want to define and discuss a few vocabulary words first that are super important in physics. The first is a reference frame. A reference frame is a choice of coordinate system that defines the starting point for measuring any quantity. This should be your first step in solving any problem. Any measurement of position, distance, or speed must be made with respect to a reference frame. So here's an example of why a reference frame is so important. Say you are sitting on a train and someone walks down the aisle. Their speed with respect to the train is only a few miles per hour. But if we looked at their speed with respect to the ground, it would be much higher. So depending on how we define our reference frame in this problem, the answer could change drastically. So anytime we approach a problem in physics, we have to first define our coordinate system, and we always must know what our starting position is, and then we can look at the problem with respect to those. I also want to define scalars and vectors. A scalar quantity is a quantity that only has magnitude or a size, but no direction. In physics, we define a quantity as anything we can count or measure. So examples of quantities are things like the length of a pencil or the number of classrooms at Franklin High School. So anything we can count or measure. So we're going to learn a lot of quantities in physics this year. So a scalar quantity is something that only has a magnitude. So an example of a scalar quantity would be an example of that could be money. So say you have 50 cents or even $5 in your pocket. That amount that you have is a magnitude or a size, and so it's considered a scalar quantity. Another example of a scalar could be the volume of music you're listening to. It could be really loud or really soft. So that volume is a magnitude and thus a scalar quantity. A vector quantity is something we can count or measure that has a magnitude or a size, but it also has a direction. We represent vectors by arrows. The length of the arrow represents its magnitude, and then whichever way the arrow is pointing gives us its direction. Here's an example of a vector quantity. Say you're explaining to a friend where your house is relative to Franklin. You tell your friend that it's 2 miles away. Well, if I was your friend, I'd be super confused because 2 miles where? It could be 2 miles north, south, east, or west. So you didn't give your friend very good directions. So, to improve those directions, you'd say something like 2 miles northeast. You would give them a magnitude, how far, so 2 miles, and you'd also tell them in what direction, so northeast from Franklin. That'd give your friend a lot better directions. That's an example of a vector quantity. So the purpose of this lesson is to explain position, distance, displacement, speed, and velocity, which are important quantities in the kinematics unit. So let's start with position first. In physics, we represent position with the variable x. Position is defined as where an object is relative to a predetermined origin. The units for position are meters. So here's an example of position. Say we have a number line and we have a group of people waiting in line at the MVA. What if we wanted to know the position of the sleeping man? Well, this is kind of a trick question. We never defined our origin in this problem. So we don't know in reference to what our reference point is. So we can't determine the position of the sleeping man. It's undetermined because we don't know where our origin is. We got to always define that first. So let's look at this example again. We have a group of people waiting in line at the MVA. We have our number line, and then we define our origin. So I'm going to define the origin as the sleeping man. He's our origin. I'm going to also define our coordinate system so I know where north, south, east, and west is. Now I can answer these questions. Number 1, what is the position of the sleeping man? Well, because I defined my origin as the sleeping man, the position of him would then be at 0 meters. 2, what is the position of the women in green and purple relative to the sleeping man? Well, the sleeping man is at the origin, so the woman in green, well, she's 5 meters west of the sleeping man. Or we often define west as negative, so negative 5 meters. The woman in purple, she's 1 meter east. We say that's positive, so positive, our answer would be positive 1 meters. 3, what are the positions of the women relative to the man in the white shirt? So now we're going to move our origin. Our origin's no longer the sleeping man, but it's the man in white at the back of the line. So we're going to look at the same women, the women in green and purple. So green, she is now 10 meters west, or negative 10 meters from the man in white. And the woman in purple, she's no longer to the right of the origin, but because we moved our origin to the man in white, she's now 4 meters west, or negative 4 meters. So as you can see with position is a vector quantity. We care not only about the magnitude or the size, but we also care about the direction. And it's super important to establish our origin right off the bat when starting this problem, starting these types of problems. Next, I want to look at distance. Distance is defined as how far total an object has traveled. The units for distance are meters. Here's an example of distance. Charlie biked 7 miles east, then 3 miles west. What is the distance he traveled? So in this example, I'm talking about my brother. He loves to bike. So I'm going to draw this example out. I'm going to define my origin, my coordinate system, and as well, and then draw out the problem. So Charlie bikes 7 miles east, 3 miles west. What's the distance? Well, distance is how far total he's traveled. So he goes 7 miles east plus 3 miles. His total distance is 10 miles. Distance is a scalar quantity, so you do not need to account for the direction because you just want to know how far he traveled total. Next is displacement. Displacement is defined as a change in the position of an object. The units for displacement are meters. The symbol for displacement is triangle X. The triangle is known as a delta, and it means change in. So it's the change in the position. So we write that delta X out as X minus X naught. Naught is that little 0 subscript. And all that means is the final position minus the initial position. So let's look at that same example with Charlie. Charlie bikes 7 miles east, then 3 miles west. what is his displacement and what is his position. So I'm going to draw my coordinate system, my origin, draw the problem out, and then I want to know his displacement. Well, displacement is a change in position. So I'm going to look at where he starts to where he ends, and I can represent that with the green arrow. So his displacement, his change in position would be 4 miles, and that vector, that green arrow, is pointed to the right, so it would be east. So plus 4 miles would be his displacement, or his change in position, from where he started to where he ended. Notice displacement has both a magnitude and a direction, making it a vector quantity. So it's really important to have that direction piece. Here's another example of distance and displacement. So say you make it to Penn Relays, and you're going to run around the track at Penn State. You start at the orange X. Travel 1 lap around the track. What's your distance and what's your displacement? Well, we know that 1 lap around the track is 400 meters, which is a quarter mile. So the total distance that you travel around the track would be 400 meters. No need to take into account the direction because distance is a scalar. But what's your displacement in this case? Well, displacement is your change in position from where you start to where you end. Well, you start on the X and you end at the X. So you're returning to your starting position, so your displacement would be 0 meters. One last example of distance and displacement. This one's a little bit more challenging. So Chris travels 6 miles north, then 4 miles east. What are his distance and displacement? So let's draw out our origin, our coordinate system, and draw this problem out. Chris travels 6 miles north, 4 miles east. What are his distance and displacement? Well, distance is the total, how far total Chris travels. So he goes 6 miles plus 4 miles, giving him a total of 10 miles. So his distance would be 10 miles. But how do we figure out the displacement? Well, displacement is the change in position, straight line path from where he starts to where he ends. So I can draw that in as this resultant line, this resultant arrow. That's his change in position from where he starts to where he ends. So how do I figure that out mathematically? Well, I can use Pythagorean theorem. So his change in position squared would be equal to a squared plus b squared. I'm going to fill in my sides of my triangle. So 6 squared plus 4 squared, and I can take the square root, simplify that and take the square root, leaving me with the change in position as 7.2 miles. Remember, the displacement, I have to have a magnitude and a direction because it's a vector quantity. So how am I going to figure out the direction from where he starts to where he ends? Well, I need to find that angle. So I'm going to use trig. I'm going to use SOHCAHTOA. I'm going to use tangent because I know the opposite side of my triangle and I also know the adjacent side of my triangle. So I'm going to plug that in. Tangent of theta is going to equal opposite divided by adjacent, which is 4 divided by 6. I'm going to simplify that and solve for theta, and it's going to give me 33.7 degrees. And then when I'm looking at that angle, from where he starts to where he ends, that resultant line is east of north. So my direction would be 33.7 degrees east of north. So my final answer for the displacement, or for Chris's displacement, would be 7.2 miles, 33.7 degrees east of north. Lastly, I wanted to find speed and velocity. Velocity is a vector quantity, and it's the rate of change of position. It's just how quickly an object moves from one place to another. So let's take the blue car. The blue car is traveling 33 miles an hour. And then according to our coordinate system, the car is traveling east. So how quickly is the car moving? Well, it's moving 33 miles an hour east. Because velocity is a vector, I have to have both that magnitude or size and direction. Speed. Speed is a scalar quantity, and it's the magnitude of an object's velocity. So because it's a scalar, all I care about is just how fast is that car moving. So in this case, the speed of the blue car would be 33 miles an hour. And that's it for today.